Hello, I'm Bahar Asgari from Georgia Tech. Thanks for being interested in our paper, which focuses on the sparse gathering, a key operation in today's recommendation systems. Recommendation systems consist of large embedding tables that are sets of embedding vectors containing users and contents features. Accessing to embedding tables is sparse. Since embedding tables are often large, they must be split over units of memory, for instance, ranks. To process a query, for instance, to suggest a music to a user, the first step that the recommender does is to read a few embedding vectors and apply a reduction operation on them, which is usually as simple as a summation that results in a single output vector. To deliver data from any units of memory to processing cores to perform reductions and then further processing them, huge amount of data needs to move from memory to the cores. To solve the main challenge of data movement, near-memory processing approaches have been proposed. They suggest moving some computing units to near memory to apply reduction on embedding vectors where data resides, and then only transfer the outcome vectors to decrease data movement. However, NMP solutions cannot effectively reduce data movement because they rely on spatial locality. In other words, the embedding vectors required for a single reduction operation are not necessarily co-located in a memory unit. Therefore, we cannot guarantee performing all reduction operations at NMPs and have to transfer vectors around. In fact, we cannot process embedding vectors where they reside because they are not co-located in memory, and we do not want to process embedding vectors in the processing cores because it causes huge amount of data movement. As a result, our key insight is that we must process embedding vectors while we gather them from any random location of memory. To see how we process embedding vectors while we gather them, let's go back to our example and consider for a second that we don't have any NMP units or any connections. For query 1, we wanted to sum V1, V2, V5, and V6. What if we have two dedicated processing elements or PEs, one to sum V1 and V2, and another for summing V5 and V6? Then we would need one last PE to sum the two results. Now that we have these three PEs, we can connect them in a tree and use them to also perform the other query. In these two examples, all PEs were always performing reduction. What if we need to apply reduction on V1 and V6? Well, in that case, the first two PEs can simply forward the inputs to the next level where they can get reduced. This tree that connects all the memory units in a memory system is our proposed efficient near-memory reduction tree, or Fafnir. Each node of Fafnir simply decides whether to reduce or to forward. Therefore, sooner or later, the corresponding embedding vectors would meet within the tree and get reduced. Another main contribution of Fafnir is that it takes advantage of embedding vector locality across multiple queries in a batch while streaming them through the tree. Therefore, not only does Fafnir fully utilize the tree to simultaneously process all the queries in a batch, but also it does that without using a caching mechanism. Each PE in Fafnir includes a few compute units that simply compare the inputs. If the two inputs are related, we reduce them and send the outcome to the next level of the tree. If not, we simply forward the inputs to the next level. In our current implementation, we connect a total of 32 ranks using 31 PEs. Therefore, one leaf PE is connected to 2 ranks. We break down the tree and implement it in 2 sizes of chips. The dim rank chips, each of which includes 7 PEs, and connect 4 DIMMs together, and only one channel chip including 3 PEs. Our proposed chips add only about 23 mW per 4 DIMMs that results in a total of about 100 mW to a 4-channel memory system, which is negligible compared to a 13-watt power consumed by each DDR4 DIMMs. We evaluate Fafnir based on a Xilinx FPGA and ASIC design at 7 nanometer. Here we evaluate the impact of accelerating the embedding lookup on the overall inference time. The diagrams in this slide show the end-to-end speedup over a one-rank system. The inference time is broken down into three parts: embedding lookup that Fafnir optimizes, fully connected layers, and other processes that are not our focus and do not change when the number of ranks increases. While for fewer ranks, both RecNMP and Fafnir work close to the ideal linear speedup shown in red line, Fafnir keeps following the red line more closely as the number of ranks increases to 32. This stems from the key difference between RecNMP and Fafnir, which is the ability to perform all reductions at NMP without relying on spatial locality. Thanks for watching. I would be glad to answer questions in the Q&A session.